Hey, what is up? We are going to jump into section 12.6 today. And 12.6 is just an extension of polar coordinates that we saw a few sections back. So let me just remind you of what the polar coordinate system was. Sometimes we had an equation, right, which could have been a circle, right, or we saw a bunch of other things like we had some roses, right? And we had some, cardioids or limacons, some other things that we dealt with, and maybe even some things like spirals, right? Where these types of equations we could not write out as functions of x or functions of y or pretty much functions of a single variable for the entire picture. Maybe for parts of the picture we could. For instance, for this circle, remember we could define the upper half of this equation as y equals the positive square root of, x squared minus 1 or whatever the radius was, and the bottom half could be y equals negative square root of x squared minus 1. Plus, sorry. Okay? But there were some things where we just couldn't really do that very efficiently, so when it came to integrating functions and working with these functions, it was easier to redefine them into the polar coordinate system. Right? And when we did that, right, what we did was we took our normal xy axis, our rectangular system, and for this point x comma y, we relabeled it like this, right, to where we found the distance from the origin to that point and called that distance r, and then the angle which starts at the x-axis and goes up to that ray right there we called theta. So this point xy, we rethought of it as the ordered pair r comma theta, right? Where, if we drop down this perpendicular right here and do a right triangle type of a thing, we could use our SOHCAHTOA stuff, and we saw that we could rewrite x as r times cosine of theta, y was r times sine of theta, and of course if we started messing around with it and looked at x squared plus y squared and simplified it, we got r squared. Or if I wanted to look at tangent of theta, that was just the same thing as y over x. Okay? All right, and that helped us do a lot of things in terms of being able to integrate some fairly ugly functions in the xy coordinate plane, right, the xy system. So now that we've moved on to using 3 variables from 2 variables, how can we take these ideas and extend them out to 3 variables, right, a 3-dimensional field, right? So let's see if I can actually draw one of these things. It's not going to go well, right? So let's say that I have some point where I come out a distance of x, go up the y-axis a certain value, and then go up the z-axis to this point right here, right? So that's x comma y comma z. Right? So there's that point in 3 dimensions. Right? What we could do is this. I could get to this point in the xy plane by doing the polar coordinate stuff. Right? I could find this distance r, this angle theta, and then still use this height of z right here. So I could call this point r comma theta comma z. All right? So in other words, we're not really changing the z variable at all, right? But we are still switching out the x and the y stuff, right? And if we mess around with this stuff, again, we can do the same substitutions. We can see that x is equal to r cosine theta, y is equal to r sine theta, and we're going to say z, if you look at how we have it set up right here, we'll say z is equal to z. Right? Not the most dramatic change, but yeah, that's the way we're going to do this. All right, so this type of system, instead of being called the polar coordinates, this is going to be called the cylindrical coordinate system. Okay? And if you go to page 732 in the book, you can see there are just a few of these equations that we can kind of see right off the top of our head. For instance, what happens if I said r equals c? Right? In other words, r is just some constant. Right? Well, in the xy plane, if r equaled some number, what that gave me was a circle in the xy plane. Right? And now, since we don't have any restrictions on z, I could let z go up and down that z-axis as high or as low as I want. So really what I'm forming here is a big old cylinder there going up and down that z-axis. So if I gave you the equation r equals 4, right, then that's going to be one of these cylinders where the radius has length 4. Right? So that's one picture that we can mess around with. Here's another. All right, maybe I'll give you the equation z equals r. Okay. So let's draw our little xy plane here. Right? And let's think about what's going on here one point at a time. Right? What happens when r equals 0? Right? Then we get z equals 0, which puts me right there on the origin. Right? If r equals 1, that means z equals 1. So what I'd do is I would go out a distance of 1 to a height of 1. If z equals 2, I would go out a distance of 2, a height of 2, and so on. So what's happening here is we're actually forming one of these right cylindrical cones like this. Of course, I could go in the other direction too. If r equals -1 or -2, then it's going to open up down here in this direction. Okay. So those are some of the pictures that we've got. Right. Let's see if we can start thinking about how we can kind of go back and forth between the regular three-dimensional picture. In other words, if I gave you a point x, y, and z, could we somehow convert that to r, theta, and z? Right? So in other words, let's go from the rectangular coordinate system to the cylindrical coordinate system. All right. So let's say I gave you this point in the rectangular system. Let's say 2 square root of 3, 2, and -1. Okay? So let's see if I can actually kind of draw this thing. Again, it's not going to be good. Let's see. So go out here, this positive value for x, positive value for y, and then down to maybe right there. Okay? So maybe that's this point, 2 square root of 3, 2, -1. Okay? All right, so how can I take this point and convert it to cylindricals? Right? Well, think back to one of the properties that we know. I know that tangent of theta equals y over x. Right? So this should hopefully help me figure out what the theta part is going to be in this coordinate system. I mean, we've got z done for us already. It's -1, but we need to find r and theta. Right? So what I can do is I can find theta, which will then give me, y and x. Well, okay, we already know y and x. But let's see what we can do here. So tangent of theta is y, which is 2, over x, which is 2 square root of 3. Obviously, those 2's cancel, so I have 1 over the square root of 3. Right? Where if you like this a little bit better using those numbers from the unit circle, if we divide the top and bottom by a 2, I get a 1/2 and then a square root of 3 over 2. Right? So what we need to do is think about my unit circle. Where is the y value 1/2 and the x value square root of 3 over 2? Right? That is, let me see if I can see this down. So I go x squared root of 3 over 2, 1/2, puts me right there. So that says that theta equals pi over 6. Right? Or perhaps it could be one of those coterminals where, if I go all the way around again, I would be here, and here, and here. Right? So theta could be pi over 6 plus any of these multiples of 2 pi. So let's call it 2 pi times n. Okay. Now, you might say to yourself, what about this one? What if I had tangent of theta equals -1/2 over negative square root of 3 over 2? That would still give me the same value we had up there above, right? Which would give me the point, let's see, right here on my unit circle. Okay. Well, it kind of goes back to this picture. Right? If you notice, this point, that's in quadrant 1. Right? When we break it down into just the xy plane. So if we go over here, which point's in quadrant 1? It's that one right there. Right? So in this case, this is what we're going to be using for theta. Right? All right, so now we know z, we know theta. Let's see if we can figure out r. And if you recall our equation for r squared, it's just x squared plus y squared. So in this case, x is 2 times the square root of 3, y is, is 2. So if we square both of those, we'll get r squared equals 4 times 3 is 12, 2 times 2 is 4. So you get r squared 16. So r gives me plus or minus 4, but since we're in that first quadrant, let's use 4. Right. So this point that we've got right here, I could rewrite that in cylindrical coordinates, writing it out as r, theta, and z, as 4, pi over 6, and then z is always just negative 1 for this point. Okay, so that's how we can go from rectangular to cylindrical. What about if we start with cylindrical and go over to rectangular? How can we do that? Okay. Well, here's a point we can mess around with. Let's see. So again, here is a point in the rectangular system. Let's say it's square root of 2, 3 pi over 4, and 2. All right. Let's convert this to the rectangular system. And the thing to remember here is that x is r cosine theta, y is r sine theta, and z is z. All right. So x is going to be r, which is square root of 2, times cosine of theta, which is 3 pi over 4. All right. So that's just square root of 2 times negative square root of 2 over 2, which gives me negative 2 over 2, which is negative 1. For y, it'll be square root of 2 times sine of 3 pi over 4, which is square root of 2 times a positive square root of 2 over 2, which is 2 over 2 or 1. And here, I'll have 2. All right. So the point in the rectangular system here, we can rewrite as negative 1, 1, and 2 in the rectangular coordinate system. Okay. All right, so now that we know how to convert points to go back and forth, what about if I wanted to start working with equations? Right. For instance, let's say I gave you this equation in the rectangular system, right? 3x plus 2y plus z equals 6. How can I rewrite this in the cylindrical coordinate system? Right. Well, the thing you usually want to solve for here is z, right? Because if you remember, z is z, right? So let's figure out how to rewrite x and y, and we'll leave z alone for now. So if you remember, x is the same thing as r times cosine theta. Right? Y is the same thing as r sine theta. Right? And then I've got my z and I've got my 6 hanging out there. So when you solve this for z, you just get z equals 6 minus 3r cosine theta minus 2r sine theta. Okay. Let's try another one. What if I gave you this? Negative x squared minus y squared plus z squared equals 1. Okay. Well, you're going to solve this for z, or in this case z squared. Let me take the x squared and the y squared over to the other side. And when you see this, hopefully that's kind of ringing some bells for you, because if you remember, x squared plus y squared equals r squared. So I could rewrite this as z squared equals 1 plus r squared. Okay. All right, so hopefully going back and forth between the two shouldn't be too bad. Okay. All right, so now let's get to some integration stuff. Just to remind you, let's remember what we've been doing. All right. We've been taking triple integrals of some function, and we're integrating over some volume, right? So we're integrating with respect to either z first, and then x and then y, or z first and then y and then x, or maybe x first and and so on, right? So we've got 6 different ways to write these things out. The way we have been trying to set them up initially looks like this, to where for this very first integral, what we'll try to do is integrate that with respect to z. All right, now again, it doesn't always work out like that. You can't always do it, but that's kind of been the first thing we've tried to do. And then we're left with just the x's and y's, which broke down into just some type of an area in the xy plane. Okay? So if we try to use this here's how we can set up these integrals using these spherical coordinates. Right? So it's still going to be a triple integral. In this case, remember x, y, and z we can rewrite as, let's see, x is r cosine theta, y is r sine theta, and z is z. Right? And then I'll do my integral with respect to z. And then what happens is when we broke it down to the x and y's, that breaks it down into just polar coordinates. Right? So once we have these set up, for these last two, I'm going to break it down into polar coordinates, which, remember, we had the r, dr, d theta technique to integrate those. Right? So I'll take this triple integral. Right? So I've got f of r cosine theta, r sine theta, z dz, and then I'll have an r, dr, and d theta. And if you remember how we want to set these things up, right? If I integrate with respect to z first, that means I have to have r's and thetas left over in the integral after I integrate it. So what I want to do is find some way to rewrite z as a function of r and theta, right? Just like we did in the previous page, right? Which means I should be able to solve for z, and I'll have z equals some function of r cosine theta, r sine theta, right? Maybe that can be my lower function. Let me call that one u1. And the upper function for z, if I call that u2, would be r cosine theta and r sine theta. Okay? So that converts everything into r's and thetas. And then remember, for r's, we can rewrite that as some function of theta. And then for the thetas, we've got some angle we start from and end from. Okay. So what we can do is I can take this and just rewrite it like so. All right, so this is a triple integral of f of r cosine theta, r sine theta, and z. And then that's times r dz, dr, d theta. And we've got these bounds that we just wrote down there a second ago. All right, so that's our strategy. So let's see how we can do this. All right, so here's a triple integral for you. Right? Here's number 10 that's in our book. Okay? We want to write, let's see, just kidding. It's number 18 that's in our book. All right? I want to evaluate this integral, the triple integral of z, over a volume. And the volume that we're given is the paraboloid z equals x squared plus y squared, and the plane z equals 4. So the way this thing looks is like this. I've got this paraboloid that goes up here. Right? And then it cuts off at this height, z equals 4. Right? So this is kind of what my picture looks like. So this is the volume that we're going to be integrating z over. Okay? So can we come up with these three bounds to use here, right? So let's start off with z first. Right? And if we look at z, every single time we look at it, it looks like the lowest point starts here on the function and it goes up to that top point, which is that plane z equals 4. So it looks like z is starting at x squared plus y squared, and it's going up to that plane z equals 4. All right, so now what I'm going to do is I'm going to take this and then I'm going to integrate over that particular area when we project this paraboloid down onto the xy plane, now that we have z taken care of. If we did x first, dx first, we'd project onto the yz plane. If we did y first, we'd project onto the xz plane. Okay. Now remember though, for z, I want this to be in terms of r's and thetas. So x squared plus y squared, if you remember, is the same thing as r squared. So let's substitute that part out with r squared. Okay. All right. Now, what happens next when we try to figure out what the bounds are going to be for the x's and the y's? Okay. Well, once we've taken care of z, we will project this thing down onto the xy plane. And if I take this paraboloid and I push it straight down, it's going to give me a circle. Right? And if you remember, this was over the plane z equals 4. Right? So this circle is x squared plus y squared, and the radius is just 4. Right? So, of course, in terms of cylindrical coordinates, x squared plus y squared is r squared. So this is the exact same thing as the equation r squared equals 4. And then if we take the square root, we get r equals 2. So if we think about my bounds for r, the smallest value for r is 0, where I don't leave the origin. And if I go all the way to the edge, my radius is 2. So my values for r go from 0 to 2. Okay? So when I start to rewrite this integral, r squared to 4 of z dz, and then I'm still going to do the r dr d theta stuff, r goes from 0 to 2. Right? And then if you look at theta, when I project this down onto the xy plane again, I'm using this entire circle. So theta starts here at angle 0, works all the way around to pi over 2, to pi, to 3 pi over 2, all the way to 2 pi. So I'm using the entire schmeal. So theta goes from 0 to 2 pi. Right? So here's how we could officially rewrite this integral. So I've got my triple integral. First one goes from 0 to 2 pi. Second one goes from 0 to 2. Third one goes from r squared to 4. And then it is z times r dz dr d theta. Right? And I'll let you all practice this thing and evaluate it, but you should get clearly 64 pi over 3. That should be your answer. Okay? All right, let's see if we can set up another one. Okay? Here is number 24 that's in our book, where it wants us to find the volume of a solid that lies between x squared plus y squared equals 1 and the sphere, the cylinder x squared plus y squared equals 1 and the sphere x squared plus y squared plus z squared equals 4. Right? So again, let me see if I can draw us a halfway decent picture. The cylinder x squared plus y squared equals 1, that starts as that circle in the xy plane and goes all the way up and down the z-axis like that. Let me give a different color to that thing. All right, so maybe I can color it red. All right, so this is what x squared plus y squared equals 1 looks like in 3 dimensions, right? It's this cylindrical cylinder, right? And then x squared plus y squared equals 4. That's the the sphere of radius 2. Let's see if I can draw this thing. Wow, that's really bad. Yeah, that's really not very good at all. Okay. Oh, good. Let me scrap that real quick. Sorry, I would go back and edit it, but I'm not really sure how to do that. I wrote down the wrong problem. Thank you. Thank you very much. All right. So here are the two equations. I was kind of mixing and matching two different problems. It was z equals x squared plus y squared, so it's that paraboloid, and the sphere x squared plus y squared plus z squared equals 2. Okay. All right, so again, here's the picture. Again, assuming I'm drawing it correctly. The paraboloid looks like this thing. The sphere, again, it's a sphere of radius square root of 2. If I draw it down here. If I draw the sphere, it's going to look like this. So the region we've got is this part right here. Right. So it looks kind of like this part right here. Right. So it's kind of the top half of that ice cream cone. Right. We're asked to find the volume for this part. Okay. All right, so how can we do that with these triple integrals? Well, if you remember, every time we do an integral, we add a dimension, right? So when I did the integral of some type of a function, just a one-dimensional function, instead of a length, that gave me an area. Right? When we did a double integral of a function, that bumped it up from an area to a volume. So what we could do to create a volume using a triple integral is, again, use these same double integrals we've got here, but then take this function and turn it into an integral, where we're going from the lower function up to the higher function. Right? And then what's left over is just, well, there's nothing there except the multiple of 1. Right? So if we want to find a volume using a triple integral, this is the idea we can use to set it up. All right, so let's see if we can do that. All right, so again, I've got z equals x squared plus y squared, and I've got x squared plus y squared plus z squared equals 2, and it gave me this ice cream cone looking thing, right, the top of the ice cream cone. Okay. So here's how we'll set it up. It'll be a triple integral using 1 integrating over this volume. Okay. So how could I, first of all, take these things and rewrite it using or as this first integral? Right. Well, if you notice, I'm going from this base, let me move this down a little bit, from this base up to that sphere every single time. Okay, so this was the paraboloid right here, and this was the sphere on top. So for the lower bound, I'll use the paraboloid, which is x squared plus y squared, and I'll go up to the sphere, where if we solve that for z, I'd have z squared equals 2 minus x squared minus y squared, or z squared equals 2 minus x squared plus y squared, which is 2 minus r squared. So z is the square root of 2 minus r squared. Right, and I guess for the bottom one, x squared plus y squared, I could rewrite that as r squared as well. Right, so then that's dz, and then we still have to figure out r and theta from here. Right. So to figure out r and theta, let's project this down onto the xy plane. So when I project it onto the xy plane, z is 0. So that leaves me with x squared plus y squared equals 2, which is that circle of radius square root of 2. Okay. But which part of the sphere am I using? I need to figure out where these points of intersection are. Maybe I'm not using that entire circle. Let's see which part of the circle we're actually using by finding those points of intersection. Right? So let's set these things equal to each other. All right. So I've got z equals x squared plus y squared, and x squared plus y squared plus z squared equals 2. Okay. So for this one, I've got z equals r squared. Over here, when I solve for z squared, I got z squared was 2 minus r squared. Right? So can we solve these two things simultaneously? Okay. Well, over to this first one, if I square both sides, I'd get z squared equals r to the 4th. So now r to the 4th equals this thing. And I can pull everything over to one side. I can factor this thing to get r squared plus 2 times r squared minus 1. So r squared plus 2, well, that's never going to be 0, right? Because that'll be imaginary. R squared minus 1 equals 0. That can factor into r plus 1, and r minus 1 equals 0. So I get r equals 1, or r equals negative 1. But let's just do it like this. Right? So I'm going from 0 out to 1, because if I went in direction negative 1, that's still the same kind of distance. Okay. So r, the second integral here, goes from 0 to 1. And then, if you notice, I'm trying to generate that whole volume, so I'm using all these different values for theta. So theta will then go from 0 to 2 pi. All right, so that sets up the integral for me. And you know what? I actually didn't evaluate that thing. So I'll let you all finish that off just to see what type of a volume that we get. Doing a little bit of work, the answer you should get looks something like this, assuming I did everything. Okay, I think it's negative 7 over 6 plus 4 times the square root of 2 over 3 times pi, which again seems pretty obvious when you take a look at it. Okay. All right, so here are some problems to kind of get you going on this stuff. All right, so here's your assignment. We are in section 12.6. Take a look at problems 1, 3, 5, 7, 8, 10, 12, 17, 20, 23, 29, and 30. Okay. Feel free to shoot me off an email. We can set up a little FaceTime or Zoom or Google Hangouts to talk face-to-face, or you can shoot me off an email. I can try to answer things that way as well. Let me know how I can help you out. You might need to rewatch a few sections of these videos a few times, need to practice some of them, but when you get frustrated, put it away, come back to it, let me help you. Again, you're not alone out there. Let me know what I can do to make this easier for you. Hope you guys are doing okay. I will see you soon.